Generative AI bias is widely treated as a downstream data problem. Feed a model skewed images, and it outputs skewed images. But the reality is a mechanical flaw inside the diffusion process itself. The architecture actively amplifies the imbalance it learns. This is a visualization of a controlled mixture of Gaussians experiment. To isolate how the model handles underrepresented data, researchers set up an ideal true distribution with a perfectly balanced 50-50 split between two modes, and then trained a diffusion model on an intentionally skewed 10-90 split. Looking at the learned score field panel, you can observe the direct result. The 10-90 ratio severely warps the geometry of the denoising process. The vector arrows representing the dominant mode physically overwhelm the minority mode, pulling the surrounding space toward the denser cluster. When you sample from this model, the resulting distribution degrades further to 12-88. The algorithm takes the original bias and mathematically amplifies it during generation. If the model's score function actively suffocates minority modes, endlessly curating massive datasets won't fix the underlying problem. Engineers must intervene at the vector level to correct the score field itself. Standard mitigation techniques hit immediate computational walls. Fine-tuning the weights of a pre-trained model is resource-intensive. Training auxiliary classifiers to police outputs introduces entirely new training pipelines and requires full access to the original labeled data. A highly efficient alternative is score guidance. It requires absolute zero retraining. Score guidance operates exclusively during the reverse diffusion phase. It manipulates the intermediate latent representations as the image forms, leaving the underlying neural network weights entirely untouched. By controlling the inference time geometry, developers can force a pre-trained model to match an exact mathematically precise reference distribution on demand. To execute this intervention, we rely on Tweedy's formula. This equation lets us estimate the final, perfectly denoised sample from any given noisy time step. Breaking down the unconditional score function reveals a convex combination, a weighted sum of conditional scores for every possible attribute. These scalar weights, prior probabilities P of AI, are learned directly from training imbalances. A severe defect occurs when one trait has a drastically lower prior probability. As the minority weight shrinks toward zero, its entire conditional score vector drops out of the equation. The unconditional score simply becomes the dominant attribute. This vanishing equation is the exact mechanism driving the mode collapse we observed in the mixture of Gaussians experiment. Minority underrepresentation is an unavoidable mathematical consequence of the fractional score weights hard-coded into pre-trained diffusion models. We can override these prior probabilities by defining an active intervention window, T. This is a specific sequence of time steps during the reverse diffusion process, where key visual features begin to emerge from the noise. Inside this window, the system performs sample tagging. Given a target ratio, the algorithm explicitly tags each latent vector to fulfill that precise distribution. Next is score guidance. We calculate an update preventing the predicted clean sample from drifting, forcing it towards its tagged mode. These guidance updates are not applied to raw pixel space. They are executed deep inside the UNet architecture, strictly within its bottleneck H-space. Operating in H-space maintains robust gradient estimation. Applying aggressive guidance directly to pixel space during early time steps corrupts the image. Conversely, H-space modifications preserve the underlying structure completely. Bypassing corrupted prior weights requires hijacking the intermediate latent path itself. The execution depends on how we generate the vectors to push them. There are two primary modalities to generate these guidance vectors. The first leverages off-the-shelf multimodal models like CLIP to align H-space vectors using text prompts. The system computes the cosine similarity between the text prompt embedding and our estimate of the perfectly denoised sample. Taking the gradient of that similarity calculation provides the physical nudge. Across multiple iterations, the H-space vector steps incrementally closer to the text embedding target. Computing this gradient on the estimated clean sample rather than the noisy input used in previous universal guidance methods vastly improves the calculation stability. Text guidance corrects the score field using pure semantic gradients, eliminating the need for labeled training data. The second modality, exemplar-based guidance, is a non-gradient alternative. It requires only a tiny subset of representative visual data, just 8 images per attribute class. First, the system runs these exemplar images backward through the model using DDIM inversion to map their intermediate latent representations at every time step. At each time step, the algorithm averages these latents to compute a single prototypical anchor point for the minority attribute. Instead of gradients, a rigid geometric update rule constrains the batch's predicted clean samples, forcing them strictly inside an R-radius ball centered on that anchor. The radius determines the engineering trade-off. A tight radius guarantees strict statistical fidelity to the anchor. A larger radius allows the vector's more lateral movement, yielding higher variance in the generated outputs. By enforcing this geometric boundary, exemplar guidance mathematically guarantees the generated samples will closely approximate the mean of the desired conditional distribution. When benchmarked against classify-based universal guidance and distribution guidance, the empirical data validates the mechanics of this intervention. This chart displays fairness discrepancy. The exemplar method achieves a massive reduction in output bias. Looking at fresh A inception distance, a critical divergence appears. Previous interventions degraded image quality to force fairness. Exemplar maintains and frequently improves baseline FID metrics. This architecture handles scaling easily. It stabilizes multi-class attributes like age ranges and cleanly executes simultaneous cross-attribute constraints, like generating a perfectly balanced split of gender and eyeglasses simultaneously. It sustains accuracy even when developers force the model to output highly skewed, arbitrary target ratios that intentionally contradicts its training set. Trading bias mathematically as an inference time geometric boundary problem allows engineers to completely bypass the computational tax of auxiliary classifiers. Building foundational models requires ingesting data at a scale where curating perfectly balanced training sets is a logistical impossibility. Generative models will inevitably learn skewed prior probabilities. However, score guidance proves that those embedded weights do not have to dictate the final output. We have a modular, modality-agnostic tool to realign generation using either text prompts or visual exemplars, requiring zero retraining. By commanding the latent geometry of diffusion models, ML engineers can dynamically override historical bias and ensure mathematically guaranteed fairness on demand.